In the last class, we were listing out simple supersymmetry algebras. So let me remember what we had in 2 dimensions. I'll just keep that on the board because it'll be useful for what we do next. So there was q plus I, q plus j. Please help me get it right. Was this p plus delta ij plus the opened out form was this, right? The zij came in the in the cross terms, right? Q minus m, q minus n is equal to p minus delta mn, and we had q plus I, q minus n is equal to z I n. Did I get this right?
Yes.
Okay. This was the algebra we got in D equals 2. In D equals 3, we got the algebra which was q plus I, q plus j is equal to p plus delta ij. Then we had q minus m. Now in this case, the symmetry is just SON. The charges are real and there's no chirality, so it's the same. So there's no plus minus, sorry. There's qi, right. So what we had, of course, was alpha, beta, p slash. So, and what had we done? We'd written them as q plus minus anyway, right? P plus, we'd written out q minus I, q minus j is equal to p minus delta ij. And was it q plus I, q minus j is equal to zij? And there was a p3 here, right? Plus p3
Minus delta ij.
Minus delta ij. Delta ij.
On zij term.
What? Negative sign. Yeah. Right? You can't multiply p with a z. Yeah. Okay, excellent. And we were trying to work out the in this case, if you remember, what we did was our spinner q alpha was q plus q minus, both for d equals 2 as well as for d equals 3. Right? We worked out various reality conditions and so on. I'm not reminding you of all of those. The net result was that q plus and q plus was self-real. That is, q plus I was a real field. Right? So q plus I was q plus I dagger. Right? I'll write that down. And same with q minus. Q minus I or m was equal to q minus m dagger. Oh, actually, just 1 minute. There's somebody who's following this course from IIT Kanpur, and he's been asking me various questions on email. So just, I can't remember all his questions, but just to put on record the answer to the one that I remember. Just 2-minute diversion. The question he asked was, it was a good question. The question was, C was a product of gammas from n plus 1 to n. Therefore, it looked like it was something that transformed like one component of a tensor. How come then instead it's like a scalar? Okay, and the answer to that question. So let me write the answer and then we'll rub that out so we can continue. The answer to that question, as we sort of said in class, but we can say it more explicitly, is it depends on how you treat C, whether you treat its indices as one upper, one lower, one upper, or both lower. Okay? If you think of it as an object with indices that are both lower, if you think of it as an object with indices that are both lower, then C is a scalar. How do we see that? You see, we have this relation that gamma mu was equal to, how did it go? C gamma mu transpose C inverse. Maybe it's a minus 1 to the power n. Right? This is, please correct me if I've got some more order wrong. Okay. So we will write this relation here as C times gamma mu is equal to minus 1 to the power n times C times gamma mu transpose. Gamma mu C. Thank you. So gamma mu C. Okay. Now, what this tells us is that you can take C through a gamma. Okay, what this tells us is that we can take C through a gamma at the expense of transposing it and introducing a sign. Now, what is the statement that C is a singlet if it transposes with both lower indices? If it transforms with both lower indices. This is the statement that if on one side you have mu nu, which is gamma mu, and on the other side you have mu nu transpose, because the second index has to transform the same way as the first index. But when we do matrix multiplication, that means putting a transpose on the other side. Okay? So this is the condition that we have gamma mu times C is equal to, so what is the condition? The condition is that under this transformation it's an invariant, so that gamma mu gamma nu, this is the change in C. Okay, so gamma mu gamma nu C, this is the change from the first index, delta C, plus, or maybe minus, we'll check that, that's gamma mu gamma nu transpose on C. This should be equal to 0. This is a statement that it's a scalar when it's treated as an object with both lower indices. Is this clear that this is the statement that it's a scalar when it's treated as an object with both lower indices? Is the statement clear? Okay? Because both indices have to transform like multiplication by gamma mu, the matrix. But when the second index transforms that way, and we write it in terms of matrix multiplication, we transpose. Is this point clear? If this equation is true, it's the same as the statement that C transforms under Lorentz transformations, like a singlet, if that is equal to 0. Okay? Now, this is the same as gamma. To show this is the same as showing that gamma mu gamma nu times C minus, because in the transposition you switch signs, C times gamma mu transpose gamma nu transpose is equal to 0. Okay? But this is true because we just take the C through all of these and they become transposes. Okay? So the fact that C transposes matrices basically is the statement that it's a Lorentz invariant when it's regarded as both indices down. Is this clear? On the other hand, had you regarded C as an object with one index down and one index up, then its transformation property would have been different. Right? Because we would have had to have an inverse transpose on the up index, and that's different. Okay, and under that it transforms like one component of a tensor. Is this point clear? I really should be asking the person who asked the question, but is it, since it was a good question, I thought I'd bring it up in class for everyone. Is this point clear? I can't.
Under mu, C is invariant, and that's what
C is invariant if with the correct action of mu.
Yeah.
Okay, mu acts on things depending on their index structure. When you regard C as an object with two lower indices, it's invariant under mu, and therefore it's a Lorentz invariant. But if you regarded it as an object that had one lower and one upper index, it would not be a Lorentz invariant. Is this clear? First index, and the second term is the transformation of the second index.
And how do you know the relative sign is plus there before?
How do you know it's plus? It's just because each term is transforming like this. See, delta psi alpha, okay, is equal to gamma mu, gamma nu, alpha beta, psi beta. That's what we have to do for each index. Okay, so the C was C alpha beta. So what did I have to do? So delta C alpha beta was equal to gamma mu, gamma nu, alpha theta, C theta beta, plus gamma mu, gamma nu, beta phi, C alpha phi.
So you should write the phi a bit right side, so that you can take the transpose, and that's what you were saying.
That's correct. That's correct. At the moment, I've just done the stupidest thing.
Yeah.
Now I'll take this on that side. And then if I want to regard this as matrix multiplication, I need to transpose. Okay? But you see there was no minus sign anyway. I know when I started doing it, I started thinking maybe there's a minus sign. But the minus sign came from the transposition of gamma mu is gamma nu commutated. That's where the minus sign came. Is this clear, Sunil? Yeah. Okay? Excellent. So, sorry. So let's go back to what we were discussing. I can't remember the guy's name in Kanpur. Huh? Pinak. Okay. I will try to answer your questions online like this. Okay. I know you have one or two more. I'll look them up and try to give you answers to the next one. Okay. Great. Pinak wanted me to answer the things in Slack. I don't even know the Slack. I've never entered the Slack. This is easier. Okay. Okay, great. So this was our algebra and d equals 2 and d equals 3, and we were in the process of writing down a similar algebra and d equals 4. I'll do that now, and then we will start looking at representations. You remember that we were looking at the following, we were thinking of our spinner as alpha plus plus times. We were thinking of spinners in this way, and you remember that this was just the plus state, it's eigenvalue under sigma 3 in the first component of the Hilbert space, and eigenvalue 1 under sigma 3 in the first component of the Hilbert space was a plus eigenvector, and eigenvalue plus under sigma 3 in the second component was a plus eigenvector. This is clear, right? You remember this. And you remember what we did? Oh, last time I think we worked out in the Euclidean space. So let's work this out for Lorentzian this time. So, okay. So the algebra was what? It was Q alpha, Q dagger, Q bar beta. Right? Was equal to P alpha beta. P slash. Was P slash. Plus delta alpha beta times I and j. We'll keep upper and lower indices. Z, I, j. remember that in this case, in these cases, the R symmetry was SO times SO. In this case, the R symmetry was SO. And in this case, the R symmetry is UN. Okay, UN is a complex, it has complex representations. And this is a fundamental under, I is in the fundamental under UN and J is in the anti-fundamental under UN. Okay, okay, great. So let's just keep going. So,
is there any delta, alpha, beta in alpha, beta index? Is it C alpha, beta?
this was just alpha beta.
No, that was what you were.
The second one, no, we don't need a C alpha beta because we've got one lower and one upper index. Because we've got, it's just the index structure of, yeah, C, exactly. Something, upper is the inverse in the transform, transforms in the inverse of the lower. Right, when you've got one upper and one lower index, you put a delta. When you've got two lower indices, you put a C. You've got two upper indices, you put a C inverse. Right, and as you say, you can think of it as a CC inverse. Okay, so we wanted to work this algebra out in detail. So first we wanted to work out the reality conditions, right? Right, so what did we have? Our equation was psi alpha was equal to C gamma 0 psi star. So psi was equal to C gamma 0 psi star. That is the equation we want to work out in detail. Okay, let us remember that in this dimension, gamma 1 was equal to sigma 1 times identity. Did we start with sigma 1 times sigma 3, I think, right? And gamma 2 was equal to identity times sigma 1. Gamma 3 was equal to sigma 2 times sigma 3. And gamma 4, this is the guy we wanted to continue to gamma 0. So gamma 0 was equal to I identity times sigma 2. Right? I'm doing Lorentzian. We worked out Euclidean last time, in the last class. Right? Okay. So this guy, I times sigma 2 was the matrix 0, 1, minus 1, 0. Right? Is this matrix? So its action on a minus gives you a plus, and its action on a plus gives you minus of minus. So action on minus gives you plus, and action of plus gives minus of minus. Okay, so let's work this out in complete detail now. Okay, so we want the we want to first look at what the reality condition is. Okay, so we want to work out this equation here. So what is C times gamma, and what was C? C was equal to the product of these two. Okay, so it was equal to sigma 2 times sigma 3 times sigma 2 is minus I times sigma 1. Minus I times sigma 1 with an I goes away, so sigma 1. Okay, okay. So let's work out C times gamma 0. Okay, C times gamma 0 is equal to sigma 2 cross, and now we get sigma 1 times sigma 2, so that's I times sigma 3, and then there's an I here, so we get a minus sigma 3. Is this clear? Okay, and so now we can work out this equation in full detail. Okay, so we work out the equation in full detail. So let's see. So on this side, we just have this expansion up there. On the right hand side, what do we get? Let's start with the guy that came from plus plus. Okay, plus plus picks up no sign from here, And from here, oh what a pain, because there are i's, shall I define C with an extra minus I? Let me define C with an extra minus I. Makes no difference, right? In all the relations, we were free to phase C with whatever we wanted. So then C times this, then this becomes I times sigma 2. Okay, so it's this matrix. Clear? Okay, so the guy with the plus plus, the first plus becomes a minus of minus. Okay, so we get alpha plus plus star minus minus plus. Now what about the second guy? The second guy is also minus alpha plus minus star, because it was plus, so this becomes minus and minus. No, with a plus, because the sigma 3 gives us minus 9. Right? Then we get, from here, we get, I'll get the sign right in a minute, alpha minus plus, this one becomes plus plus. Now minus became a plus with no sign, and plus stays plus with no sign, so I get plus here. Okay? Please correct me if I make a mistake. Okay? And finally we get plus acting on that guy there, we get plus minus alpha minus minus star, and minus became a plus with no sign, but minus picks up a sign here. So the right hand side was this. Do you agree? Okay, and so we conclude that alpha plus plus is equal to alpha minus plus star. Everything here was star. Okay, alpha plus minus was equal to minus alpha minus minus star. Okay, alpha minus plus was equal to minus plus minus alpha plus plus star. Okay, and alpha minus minus was equal to minus alpha plus minus star. I've done something wrong. Plus plus was minus plus star, and minus plus was plus plus star, but I've got an extra minus sign. Just a minute. What? It's a complex representation, that's correct. It's no, that is fine.
That extra minus sign should be there, right? Because it's complex.
No. It should be, there should be an extra minus sign if it's pseudo real, right? Right. Just a minute. What's going on with this sign? It should, of course, mix chiral with antichiral. That it's doing. But it should have been possible to impose this condition. What have I done wrong? Just one.
I'm getting the minus sign in the first.
You're getting minus sign in the first equation. I probably just done it wrong. So thank you. So that let's check. First equation, I'm equating coefficient of plus plus and plus plus. So you got this as minus, Siddharth?
Minus plus. Yeah. So I got alpha plus plus equal to alpha minus plus.
Yes. So let me check this. So if I act with you're getting the same as me? If I act with I sigma 2 times sigma 3 on minus plus. So this guy is a plus and this guy is a plus. Yeah. Oh, what? Sorry, give me a minute. What have I? Yeah. Right. What have I done wrong? Just, is this what I should expect? Sorry. What have I done wrong? Sorry, give me a minute.
In the star equation, C comes alone. What was the logic that you can take any I?
If we put i's in all of these, it won't change anything, right? Because suppose I put an I here. Suppose I multiply all of these with I. Then when I take the complex, see, the question is whether this equation is consistent with this equation, right?
Oh, that doesn't.
If I put an I here and I put an I here, then if I complex, so let's try. The problem we're getting is that this is inconsistent, right? If I suppose I had alpha plus plus is equal to I sigma alpha I minus plus star, and we had alpha minus plus is equal to I minus I, alpha plus plus star. Now if we take complex conjugate of the of let's say the second equation,
You take one single complex.
We take alpha minus plus star is equal to I times alpha plus plus O. What was the oh, this is strange. It's strange. Sorry, you're probably right. Give me a minute. It's strange because there. Yeah, exactly. Yeah, so it can't change by doing these kind of things, right? Sorry, I've messed up somewhere. Sorry. Just give me 1 minute more. I'm doing something stupid, right? What am I doing? The point was that since isn't the point that since I've got a complex representation, I could always multiply C by gamma 5. Will that help? Just a minute. Just a minute. I think that will help, you see, because then that, you see, let me modify my C. We never looked at complex conjugation, complex representations very carefully because it was always guaranteed to work. The reason it was always guaranteed to work is this sign doesn't work out. Let's multiply it by gamma 5. Okay.
With the C gamma.
What?
With the C gamma not you are
I'll just change C to be gamma 5 with an extra factor of gamma 5. Okay? What is the point? The point is that gamma 5 acting on a chiral spinner is a plus, but gamma 5 acting on an anti-chiral spinner is a minus. So then half of these equations will change sign. Yes? C was I got it wrong. Gamma 3, gamma 0. This times this, which was, yeah. What? Sigma 2 and sigma. And then I took gamma naught. That was sigma 3. But you see, it can't not work with complex spinors. Why can't it not work? Let me just put C prime is equal to gamma 5 times C. Okay, if it's not working with C, I'll put a gamma 5 times C. Okay, so let me just do that. Okay, now gamma 5 we know has the property that if it's a chiral spinor, we'll get a plus sign, and if it's an anti-chiral spinor, we'll get a minus sign. Okay, so here every time we obtained in the end an anti-chiral spinor, we should get a minus sign. Okay, so we get this, nothing here, this. All good? Okay, so now we get, compare now the coefficient of plus plus and minus, and plus plus was here. So we have plus, minus plus star, this is okay. The coefficient of plus minus is now this. The coefficient of minus plus is now this, and the coefficient of minus minus is this. So every sign is plus now. So now it works. Okay, so this is the reality condition I'll impose. Okay, the point was here that because it was two representations rather than one, we have more flexibility. Okay, and that's what this gamma 5 allows us to do. You see, the chiral spinor, the spinor was a chiral and an anti-chiral thing. We have one more thing that commutes with Lorentz invariance, the Lorentz matrices, namely gamma 5, because we've got two representations. Okay, and that's what helped us get away with it. Okay, excellent, thank you. So this is now our reality condition. Is this good? Okay. So you see, the final rule is the following. The first index is being flipped by reality, and the second one is not. Okay. Now, what was the distinction between the first and the second indices? You might think, on the first indices of the second indices on equal footing. Not quite, because the first index was created out of these two gammas. Okay, this sigma 1 and this sigma 2. And the second index was created out of these two, and this one has this extra I. Okay, So the second index was created by a pair of gammas, which include the one that we analytically continued to Lorentzian. Okay, so the rule is that the gamma that we analytically continue to Lorentzian, that guy behaves different. That plane behaves different. Okay, and we're seeing that complex conjugation does not flip the sign of angular momentum in the plane where you analytically continued gamma. But it does flip the sign of angular momentum in the plane where you've not. This is completely reasonable, right? Because in the plane where you've not, it's Euclidean. So 1 plus I2 becomes 1 minus I2 under complex conjugation. But in the plane where you've flipped, 1 plus 2 stays 1 plus 2. Right? It's the difference between Lorentzian light cone, which is real, and holomorphic, which is complex. Okay? Excellent. So now that we understand these reality conditions properly, now let's write down the supersymmetry algebra for this case. Okay. So we just have to write out the algebra, and okay, first let's just write it out and then understand it in more detail. First, let's look at this this guy alpha beta. Okay, so okay, first let's look at this. Let's look at this index. So we want to open out p slash alpha beta. Okay, so what does p slash alpha beta mean? Well, this is equal to p1 sigma 1 slash sigma 3 plus p2 I slash sigma 1, okay, plus p3 sigma 2 slash sigma 3, okay, and then plus p0. Okay, I'm working with p above, so everything is plus. Okay, plus p0 I into identity slash sigma 2. Okay, and I'm not going to open this out any further. We could write this as some big 4x4 matrix. Okay, I'm not going to open it out. For any component we need, you just plug in here. Okay, and in addition we have this delta alpha beta piece. We have plus I slash I, that's what delta alpha beta means. It's just identity in both places. Okay, times Zij. Okay, now this we can open out, and we will in 2 minutes, but only for the thing that we want to do. Okay, as you see, if you try to be completely explicit as you go to higher and higher dimensions, it gets messier and messier. The compact general notation is very nice. It captures quite messy algebras. Okay, excellent. This is all I wanted to say about just showing you explicitly what these. Here, we will in a bit open out and see what reality does in a little bit. Okay, but in the special case of interest. Okay, fine. This is all I wanted to do for explicitly writing out these supersymmetry algebras in low dimensions. Any questions or comments before we proceed? We're now going to move on to try to find representations of these algebras. Okay? First, okay, great. So now, in the rest of this lecture, we're going to find representations of supersymmetry algebras. And there are 3 cases that, so what does it mean? find representations of supersymmetry algebras. Yeah.
Sorry, why you remove the I for the gamma naught? The P also has.
Where did I remove I?
P also has. The gamma naught has had an I.
Yes. I removed it here. Sorry.
Oh.
I should have added. It was there. Thank you. It's not intentional. Okay. Excellent. So let's continue. So what does it mean that we want to find representations of supersymmetry algebras? You know, when we're studying quantum field theory in Poincare space, single particles, there is this beautiful classification of single particle representations, and then also multi-particle, but that's sort of like Fock space. So, but single particle representations of the Poincare algebra. And this classification, all of you know, but I just remind you of the main idea. The main idea is that first you have to choose a momentum. Okay? So representations are fields, and fields are functions of momentum. Okay? But you choose a momentum, and then at any given momentum, you have a bunch of objects representing your algebra. And that bunch of objects transforms in an irreducible representation of the part of the algebra that fixes that momentum, that commutes with that momentum. That part of the algebra is called the little group. Okay? And for massive particles, for the Poincare algebra and d spacetime dimensions, you know that the little group is SO d minus 1. How do you see that? Because the momentum of interest is the momentum of a massive particle, so it's time-like, so you can always move to a frame where it's time. And then the part of the rotation group that commutes with time is spatial rotations, and that's SO d minus 1. For massless particles, the part of the little group that commutes with the part that acts non-trivially, there's an extra U1 that ends up doing nothing. Okay, so the part that acts non-trivially is SO d minus 2. Right? And how do you see that? It's basically because your momentum is now light-like. So you ask for the part, you take P plus and P minus. That gives you a two-plane. The part that commutes with that two-plane is SO d minus 2. Then there's some extra U1 that does some rotation in this two-plane. As you probably remember from your studies, that part was, though it's there in algebra, it ends up doing nothing for representation theories. Let's forget about it. So the net effect is that we've got this, if we choose a particular momentum, we've got this little group which is SO d minus 1 or SO d minus 2. And then what the representations of SO d minus 1 or SO d minus 2 give you the representations in which physical particles, physical states of a physical single particle states transform in this Poincare algebra. Then there's also this way of, there's a way of taking this SO d minus 1 or SO d minus 2 and boosting it to some other frame. So if you're not in the frame where P is rest, how do you get that matrix there? Okay? So the net result was that the representation space is some irreducible representation of the little group, which is SO d minus 1 or SO d minus 2, times functions of momenta. And on this space, you have a full representation of the Poincare group. I'm not going to review this. This you probably know. Right? So, wonderful. This is the sense in which we want to find representations of the supersymmetry algebra. We want to find how single particle states are grouped together in representations. Okay, now single particle states will, as before, be labeled by their momentum. Okay, but now we've got this bigger supersymmetry algebra. So what we need to do is to look for the part of the supersymmetry algebra that stabilizes this momentum.
It's true that little group is just the stabilizer of this moment.
It's true for massive particles. For massless particles, there's the extra U1, right? Okay. It's effectively true, right? Okay. So what we've got here now is, you know, some sort of a supersymmetry algebra, and the supersymmetry is like the square root of the momentum. Okay, so what we're going to do is to look at a particular momentum, just like we did for little group theory, and study the supersymmetry algebra and see what happens to its representations. Just like for the Poincaré group, you looked at a particular momentum and then looked at the part of the Poincaré group that didn't change that momentum, okay, and looked at its representations. This is the game we're going to play. Is this clear? Excellent. So I'm first going to tell you structurally how it works. Structurally how we're going to get how this works, and then we'll look at a few examples to try to see in detail how it works. Okay. Let us start. You know, there are going to be 3 cases of general interest. So the first case will be light-like momenta. The next case will be time-like momenta, so massive, massless, generic, so massless, then massive and generic, and massive and BPS. Okay, and we're going to study each case separately. Okay, let's start with the light-like moment. Okay, so first I'm going to tell you schematically how it works in every dimension, then we'll try to unpackage this in more detail. Okay, suppose I've got some P plus, some light-like momentum that is turned on and is non-zero. Okay. Now, how is my supersymmetry algebra going to look? The supersymmetry algebra is going to look as follows. You're going to get Q. Okay, so first thing we're going to do is this P plus is part of a particular 2-plane. So we take our gamma matrices and we make these 2 planes as we've been doing. The P plus is part of a particular 2-plane, the 2-plane that involves gamma 0, the guy we've analytically continued. Okay, now this Q here carries spinor charges under each rotations of each of the 2 planes. These are the plus minus in these factors that we've been talking about before. Right? And the charges under sigma 3 in each of the tensor product factors. Is this clear? So Q, a basis for all the spinors, is given by specifying what its charges are under sigma 3 in each of the tensor product factors. Okay, so suppose we had a Q in, I don't know, 8 dimensions. Its basis you could label it by alpha 1, alpha 2, alpha 3 and alpha 4, where alpha 1, alpha 2, alpha 3 and alpha 4 were each plus or minus. This is clear? Just like we did for here. Okay, this was part of the purpose of doing these special cases. So you understand, right? If we had some 8-dimensional, there would be plus minus the first factor, plus minus second factor, and so on. Okay, so that's what the spinor labels are. Now the last factor is the one under which we've done the analytic continuation. Okay, so the supersymmetry algebra is going to always take the following schematic form. Okay. I get 0 because I've turned on a p plus but no p minus. Because I've got a light-like momentum. If I have both p plus and p minus, it would be time-like. Okay?
You are specifically taking a momentum which is p plus.
Yes. I'm specifically taking a light-like momentum, and I'm choosing it to be in this particular two-plane. Has to involve time, and I choose it for convenience to involve the second direction I paired with. Because this is a choice of basis, of course. Nothing very special. Okay?
No, absolutely no difference between these two choices.
What?
P minus and p plus.
P minus and p plus, no difference. Just, yeah. I'm choosing p plus, I could choose p minus. Yeah, I'm calling it p plus. Now, p plus, I could take as p 2n minus 2 plus, sorry, p 2n minus 1, p0 plus 2n minus 1, p 2n minus 1. P minus I'm calling p0 minus, but that's really no difference. Right? It would just flip which one was 0 or not. Okay? And then what remains could have central charge contributions. Okay? But we're going to assume that those, to start with, we're going to assume we have no central charges. Zij's are all 0. Okay? You will see, we will deal with central charges when we look at BPS algebras in a moment. Okay? So,
Alpha beta, if these alpha are same.
Yes. No, not necessary. So this will now be some, let's call this whole thing alpha and this whole thing beta. This will be C alpha beta. That's C alpha beta. Okay, but now there's a dagger. So delta alpha beta. Delta alpha beta, because this is a daggered index. Okay, we'll do this all, we'll look at it all carefully in a moment. There'll be some index structure with the remaining spinor directions. So this will be some 6-dimensional spinor index structure in our particular example. Because of these spinors, one direction, this plus minus, has been eaten up. Is this clear? Okay. Now, this guy just gives 0. Okay, so it has no index structure. 0 is interesting. Okay, and let me just write down the last part. Okay, and anything that will be like 2 plus. Okay, right. At the moment, I'm just going to write it without the daggers. Okay. So then this will be like a C alpha beta. C alpha beta. But it's equivalent to writing it with the daggers, because as we've seen in this example, starring does not change the angular momentum of the direction involving 0. Okay, so starring will change all the other indices around, but will not change the angular momentum of the guy involving 0. This is just a general thing, right? Because light cone momentum in Lorentzian space is real. Okay, so we will get this structure, and then we also get q alpha, let's say, plus q beta minus. This is because there are no central charges. This is equal to 0. Now you see that we're going to get this kind of structure is obvious. Why is it obvious? We've assumed there's no central charge. So the only thing that could appear on the right hand side is momentum. But we have only one momentum. And that momentum carries charge 1 under rotations under this 2 plane. So the only way you could get something non-zero is if you have 2 pluses. Because the only thing on the right hand side is something of charge 1. So the only possible guy that could give you something non-zero is these 2 pluses. Clear? Okay. Now we use the next fact. The next fact is that under complex conjugation, the complex conjugation of a plus remains a plus in this last index, and the complex conjugation of a minus remains a minus in the last index. So the fact that these guys are 0 tell you that Q anti-commutator Q daggers are 0. Because you see the dagger of something here is also a minus guy. Because the reality condition will ensure that. So all minuses with their own daggers have 0 anti-commutator. Now these have to be represented in a unitary theory. The only way they can be represented is by being 0. Okay, so we've got operators in this representation that obey operator anti-commutator with operator dagger is equal to 0. The only representation in a unitary theory for this kind of thing, because this is positive definite, the only representation is that these guys are 0. Okay, this tells us that in our representation space, these guys will be equal to 0. And therefore, this part of the algebra will be trivial, because one term here is 0.
You are saying because Q minus doesn't mix with anyone and it's positive definite, so every component should be 0.
Exactly. We can make make linear combinations here. So we take a Q minus and its dagger anti-commutator is 0. Because the dagger of every Q minus is a Q minus.
Yeah.
Okay? So we can choose any Q minus, choose its dagger, that anti-commutator is 0. But that's positive definite. So it has to be 0. Okay, it's greater than equal to 0. It's not positive definite, it's positive.
If you had central charge,
then things get more complicated.
Yeah.
We'll come back to that.
Because they are decoupled and positive definite, that's why.
Exactly. Yeah, it's turning on central charges always makes the representations effectively massive,
Yeah. Okay.
as we will see. Okay, so right now let's forget about the central charges. So what is left is this guy here. Okay, now you see that what's left is we have to implement this algebra of Q's with itself, okay, itself also including its own dagger, if you like, being equal to C alpha beta. Now, does this remind you of anything? So just throw this guy away. These guys are gone. Does this remind you of anything? We can always scale all these operators with the 1 by square root p plus. So effectively it's sort of like Q with Q is equal to 1. If we take, we can multiply by C on both sides, and we get Q with CQ. We'll do some starring and so on. But anyway, we'll get effectively, it's some anti-commutation of an operator with itself, which is equal to identity. Right. This is very similar to what we do when we look at Clifford algebras. Right, we have anti-commutator of gamma mu with gamma nu is equal to delta mu nu, 2 times delta mu nu. Okay, as Schumann said, basically what we've got is some fermionic Hilbert space. Okay, so what's going to happen here is simply this, that we take the total number of Q's here and break the total number of Q's that remain here and break them up into creation and annihilation operators. We start with some ground state vacuum, some vacuum where nothing is filled. We act with all the creation operators. Okay? And this gives us some effective Hilbert space. Now, suppose we started with a certain number of supersymmetries. Suppose we started with a certain number of supersymmetries. Half of them have already been removed because we're removing the Q minuses. The remaining half have to be divided up into creation and annihilation operators. Okay? The remaining half have to be divided up into creation and annihilation operators, and then you build some sort of Hilbert space out of these. It's easy to count the dimension of the effective Hilbert space. 2 to the power, whatever, total number of supersymmetries divided by 4. Half removed and then half for annihilation and creation and annihilation. Okay? But more seriously, one can count the full representation content of that space. Okay? How did we get the representation content of Clifford algebras? How did we get the representation content of Clifford algebras? Well, you remember that the representation content of Clifford algebras was everything. Okay, when we looked at a Clifford algebra, which was sort of gamma mu gamma nu is equal to delta mu nu. Okay, we could build up this whole space by breaking up these gamma mu's and gamma nu's into creation and annihilation, and then acting with creation for each of these. Okay, that in the end, that quantization gave us one representation which was a spinor. Sometimes it gave us two representations, chiral and anti-chiral spinor. Okay, what's the difference now? The difference is that the gamma is transformed in the vector representation of SOD or SOD minus 2. In this case, the objects that are making up the Clifford algebra transform not in the vector representation, but in the spinor representation. Okay? So it's like we're making a Clifford algebra starting not with gammas in the vector representation, but gammas in the spinor representation. When we did this with gammas in the vector representation, we produced the state content was either 1 or 2 spinors. When we do this with gammas in the spinor representation, we get some other state content. What we get will depend in detail, depend on dimension and so on. Okay? But you can take this, and we'll look at examples, and take the state content, quantize that algebra. Okay? We can take that and we'll get some set of representations. Some sum over reps of SOD minus 2. Is this clear? Is it clear that this is the structure of what's going on? Okay? We will look at many examples as we go. Okay. Now you might think, okay, great. So quantizing these Q's has given us some state space. So are we finished? Answer is no. Okay? Answer is no, because you see these Q's, what is the remaining algebra that's left? The remaining algebra that's left was these mu nu's which were part of SOD minus 2. Mu nu with mu nu, m alpha beta give you the SOD minus 2 algebra. This, of course, we know. Okay, so quantizing this part will look for irreducible representations of SOD minus 2. This is just like in Lorentz group. The spin of your representation, this is the usual little. And quantizing this part Q with Q we've just understood. Spinorial Clifford algebra. But there is another issue, which is that M with Q is not 0. Okay? M with Q is not 0, but it's sigma mu nu M mu nu in the spinorial representation. Q transforms under SOD minus 2 rotations like a spinor does. The sigma mu nu is gamma mu in the usual spinorial representation matrix. Right? It's commutative gamma mu. Right? So you see that had it been that this part wasn't there, the algebra would have been a direct product of the algebra generated by Q's and the algebra generated by SOD minus 2. And so the representation would have been a direct product. Okay? But that part is there, so what are we going to do? Okay? Now, what we do is the following. Okay? What we do is the following. We use the fact, so let us remind ourselves that gamma matrices by 2 or maybe by 4 with gamma alpha had vectorial type representations. This was equal to delta mu alpha gamma nu minus delta nu alpha gamma mu, maybe with some signs. And the gamma matrices transformed like a vector under the representations mu nu built out of gammas. This you know. Okay. Now you could ask what did we have to do? What did we have to do here to these to these gamma matrices to get this particular representation? Okay, and what we did is just the following. We take this. Okay. We take the adjoint the representation of mu nu in the fundamental representation. Okay, and what am I saying? Sorry. Yes, ma'am. Right. What I want to say is that when we did ordinary Clifford algebra, we had a representation. We could build a representation, matrices that would make any gamma alpha transform under SOD just out of elements from that Clifford algebra. Right? That's what this equation says. Okay? So we're going to try to do we're going to try to do the same thing here. We're going to try to do the following. We're going to take sigma A mu nu. Okay? Q. This will be sigma Q alpha Q beta, all these will be the pluses, Q beta plus and I will try to put sigma, just a minute. Mu nu, and in this representation. Okay. Okay, so I take the generators of SOD minus 2 in the spinorial representation. Okay, I take the generators of SOD minus 2 in the spinorial representation. Okay, and I multiply them with Q alpha, Q beta like this.
And all these are pluses.
These are all plus, everything. This is all SOD minus 2 now. Okay, now if I take this and I do Q theta, because roughly speaking, you know, I have to get all the C's and so on, right? But roughly speaking, because you will contract one of these with this, what this will give you is sigma mu nu alpha beta Q beta. This is actually exactly what we did here. You see, the generator of SOD minus 2 in the vectorial representation was just the antisymmetric matrix like, you know, M mu nu alpha beta was equal to delta alpha mu delta beta nu minus delta alpha nu delta beta nu mu. And then plugging this with, what did I want to do? Gamma alpha, gamma beta is the same as that. Factors of 2. Is this clear? Okay. This is how we obtained the construction so that using these objects within Clifford algebra, we could find the charges that would make gammas transform in the correct way directly from commutation relations within Clifford algebra. Is this clear? Okay, so now that we've got this working, go on.
Here you are writing the left hand side is like matrix components. Like each matrix component you use.
This guy, and then I multiplied it with gamma alpha, gamma beta.
Oh.
And then that gave us this.
That.
Right? That was how we realized, how we figured out what the generator of SOD minus 2 should have been. Because gammas had to transform like vectors. And this will ensure that they do once you use the Clifford algebra.
It's multiplied with only one gamma.
No. 2 gammas. We want the generator of SOD minus 2. So this, if we just multiply this out, we will get gamma mu, gamma nu, minus gamma nu, gamma mu. And that's that generator up there. Is this clear? Okay. So in the same way, we can make a construction here, which will be effectively take this sigma. Now not, the thing that replaced this was mu nu, not in the vector representation, but in the spinor representation. Okay, that's this sigma mu nu alpha beta. Then you multiply with the q alpha and q beta. Okay, and you will then, by using this algebra, then by using that algebra, the algebra right on top there, be able to show, we have to do this, and we will do this carefully in special cases, and even more generally. But first I want to give you the general idea. We will be able to show that this commutation relation is this. And you know, the basic idea is up to these index issues, it's just weak contraction, right? Because the algebra tells you that two q's contract. What's left over is sigma times q. Is this clear? Okay. Therefore, we can now do something quite interesting.
So q's contract to give what? P?
To give 1 basically. Right, because now, okay, we've rescaled the q's with p plus. So it's just 1. Okay, right. Okay, so now, what's, yeah. So now we can do something quite interesting. And the interesting thing we can do is the following. Let's call this guy, this construction, this object, we'll call it n mu nu. Now do you say that m mu nu minus n mu nu anti-commutator q alpha is equal to 0, or let's write, and we'll call this minus thing, we'll give it another name. Let's call it h mu nu. Is this clear? Because m rotates q's as if they're spinors. N does the same by construction. So m minus 1, n leaves the spinors unchanged.
Yes.
Okay? So now we have, by choosing, doing something interesting, we've created, moreover, since m mu nu obeys the SOD minus 2 commutation relation, and n mu nu obeys the SOD minus 2 commutation relation, m mu nu minus n mu nu also obeys the SOD minus 2 commutation relation. It's just two distinct SOD minus 2s. Therefore, h mu nu obeys the SOD minus 2 commutation relations. Okay? And therefore, we have separated our algebra. So our algebra now, in terms of these new constructions, we have h mu nu, h alpha beta is equal to SOD minus 2 comm relation. What? M mu nu and n mu nu. Right. Good point.
They may not commute, but
Yeah. Good question. Let me get that straight. Sorry, just a minute. Right. Give me a minute. Good question, sir. Just him.
I
Yes?
think it just cancels out. If you take a minus b, right? That's it.
Ah, is that right? Okay, let's see. So you say A minus B, A mu, let's see. Okay, you say we get M
Minus n comma n, the cross terms cancel. Minus n comma n, minus n comma n.
minus n comma. And what about the fact that two of them are mu nu and the other two are alpha beta?
But if you exchange,
Just a minute. Just a minute. Let me see one. So interesting. Thank you. What they did was, it's spelled the same thing. Same thing. Let me stop this again. Sorry. Let me define M mu nu. Okay, we had these, let's give these guys a name, 1 by 2p plus q sigma q. Let's call these r mu nu, whatever. H mu nu. Okay, so what they say is, let's define q is equal to L mu nu plus H mu nu. So I suppose it's the same as what I had. And I'm going to figure out the rules for what?
capital N or L?
L. They've written L. Just a name. M is the full SOD minus 2. What?
There was an
N.
n.
We'll call it N. Okay, sorry. Yeah. Okay. So, and this is a suppose we make this redefinition and postulate the following. We postulate that N with N is equal to SOD minus 2. N with Q is equal to 0, and Q with Q is what it should be, right? Omega times I, let's say identity. Okay. Now claim if we do this, then original M obeys the correct commutation relations. This is true, right? Because if you have N that anti-commutes with Q, okay, so, right, sorry, there was plus rather than minus, sorry. So let me say it again. We have the original SOD minus 2 algebra. We're going to define a new algebra, N, which is postulated to have these properties. Just an abstract new algebra. Point is that if N has these properties, then the original M and Q have the right commutation relations. Okay? Here, because N by definition commutes with Q. So now this with this, now the M with M commutation relation works. Okay, your objection goes away, Sunil. Right, because there's no cross term, because H was built out of Q's, and L by definition commutes with Q's. Okay, so this construction gives you the correct M with M commutation relations. It also gives you the correct M with Q commutation relations, because N commutator with Q is 0, but H commutator with Q is the right thing. Okay, so if we had an algebra like this, then we can construct out of this algebra the algebra we want, simply by identifying M is equal to N plus H. Is it clear? Therefore, representations of the original algebra, to find representations of that original algebra, is the same thing as finding representations of this algebra. Okay? And representations of this algebra then are labeled by irreps of SOD minus 2, also of R symmetry. I have not been keeping track of that, but also of R symmetry, SOD minus 2, R symmetry, and whatever you get by this quantization. But that is something definite. That's just quantizing the spinorial Clifford algebra. Is this clear? Okay? So this is the abstract labeling of irreducible representations of this algebra. But you know, we're not interested in N. N is not the physical guy for us. The physical guy for us is M. So suppose I give you a representation. So suppose I give you some representation of N. I'm not keeping track of the R symmetry now, but we will when we do examples. I'm just keeping track of the SOD minus 2. Say that N is in some representation of SOD minus 2. Let's say R1. And when we find the state content of this, we find some bunch of representations of SOD minus 2. Let's say R tilde 1 plus R tilde 2 plus R tilde 3. Suppose. Okay? Now, we want to know what representations of M appear. M is the true angular momentum of our problem. But now what we have is that M is the angular momentum that is made up of angular momentum of two completely commuting spaces. So this is the same problem as Clepsch-Gordon. If I give you a representation in one space and a representation in the commuting space, and my angular momentum generators are the sum of the generators in these two spaces, then in which representations do you get? That is Clepsch-Gordon fusion of representations. So what we're supposed to do is to take this, tensor this, and decompose the tensor product into irreducible representations of SOD minus 2. That will give us the representation content under M. Is this clear? So representations are labeled by choosing an SOD minus 2 representation, irreducible and at will. But this is now the representation of this N. In addition, we get a bunch of representations from the spinorial Clifford algebra of Q. Those are unavoidable. Okay? And then finally, what we're supposed to do to get the so these are the labels for representations. But if you actually want the state content in terms of actual spin, you're supposed to take the product of these two representations in sense of Clepsch-Gordon, and then whatever you get on the right hand side is the bunch of representations that actually occur in your under spin in your physical theory. Now each representation of mu nu that actually occurs is a particle field. It's a representation of the Lorentz group. So the end result of all of this is that a single representation of supersymmetry is a bunch of ordinary Lorentz particles. But you can't have one without the other. They all come together. Is this clear?
change the basis to make it block diagonal.
Which basis?
You wanted to do full MU representation.
Yes.
And then you split it into two block diagonal parts.
Two commuting paths. Not, yeah, right, yes. Two like tensor product kind of. We made it, we've defined a new space and some new abstract space on which there is a new abstract SOD minus 2 generator. Okay, which by definition commutes with spinors. Okay, we pick a representation in that space that we're free to do arbitrarily. No, nobody can tell us what to do. We choose that. Then we get what we get from this decomposition of the spinorial kind of Clebsch-Gordon. We get what we get from there, and then we have to fuse the two to get the final representation content. So fuse the two in terms of, in the sense of Clebsch-Gordon decomposition. That gives you the final state content under SOD minus 2. But SOD minus 2 state content, irreducible representations, each irreducible representation of SOD minus 2 is a particle. So it gives you the final particle content of our theory. Okay, this is the general procedure to build such representations. Is this in broad terms clear? We will see many examples. End of this class, next class.
This is similar to like in the 4D Lorentz algebra we do SU2 plus split.
Okay, very good, yes. Though that was easier because it was automatically split. Here we had to do a little mixing. Yeah, SO4 was SU2 times SU2. Here we had to do a little mixing to make it split.
Sorry, where is the mixing?
The mixing with H. Right, the original M did not split.
Oh, yeah.
We had to be a bit cleverer. Is this clear? Okay, since we've gone so far, let me also tell you in these rough terms how it's going to work for massive representations. Okay, for massive representations,
You can do it for SO4 also.
what?
You can do it for SO4 also, this exercise.
Yeah, we will do it for SO4.
And then that will be an equivalent decomposition like SU2 process.
Like SU2 times SU2.
It's another decomposition.
Yeah, there will be two SO4s.
Yeah.
Each SO4 has its own SU2 times SU2. So suppose we were doing 6-dimensional like representations. The SOD minus 2 is SO4. That happens to be SU2 times SU2, but we don't need to use that fact. Then there's one SO4.
Understood. I'm saying that the trivial example we know is SU2 plus SU2. This is another example of decomposing.
This is another example and a less trivial example. Because you have to mix things, right? Right? Yeah. Fine. Basically what we're doing is making the full angular momentum space the direct product of what you get from Clifford algebra and something else that commutes with the Clifford algebra. Okay? And that gives us what we want. Okay. When we work out massive representations, in the end, everything will go through except SOD minus 2 will be replaced by SOD minus 1. Okay, we get the same kind of procedure if we turn off central charges. We get the same kind of procedure. Now, the first really big difference between massless and massive representations is the following. For massless representations, we saw that half of the supercharges were inactive. The Q minuses squared were just 0. Okay, so the algebra that we're representing is an algebra involving only half of the Qs. For massive representations, there's no analog. Okay, all the Qs will be active. So the Clifford algebra that we will create will come from all the Qs. Okay, now first question, and finally, where the last kind of representation is the one that we get, including masses and central charges. As I will show you, it's sometimes possible to arrange the masses and the central charges so that half or some fraction of the supersymmetries become inactive. Okay? So these representations once again become short. Okay, so the light-like representations are shorter representations than the massive representations because they involve quantizing a smaller Clifford algebra. Okay? Massive representations are long representations. However, there are special massive representations where the mass and the central charges are tuned so that these once again become short representations. These are BPS representations. This again we will see in some detail. Okay, so is the general picture clear? Is the general picture clear? Okay, good. So then let us proceed. Okay, 2 or 3 generalities before we start looking at examples. First generality, you see, I told you that we were free to choose whatever representation we wanted here, but this part was not in our hands, right? It's just what it was. Right? So now if we want the shortest representation possible, this whatever representation we are free to choose here, well, the natural thing to do is just to choose the trivial representation, identity. In that case, the particle content is just whatever we get out of Clifford algebra. Okay, so the shortest representations in the game are those that we will get out of Clifford algebra. Clear? Okay. Now, one other general point that's sort of good to keep track of. Suppose we have a theory where the total number of supersymmetries is suppose we have a theory where the total number of supersymmetries is 4n. Okay, for instance, in 4 dimensions, the minimum number of supercharges is 4. But if you have flavor indices, these R symmetry indices, it can become 4, 8, 12, 16. So suppose you have a theory where you have 4n supersymmetries. Now, question: what kind of spins are going to occur in a representation of supersymmetry? Let us, to start with, look at the minimal representation of supersymmetry. Namely, the one where we've chosen this representation R1, which was in our hands. We just choose that to be trivial. Okay, so we look at this representation. Question: what kind of spins are going to occur? So you remember that what we did was to choose half. Okay, first let's say we're doing light-like representations. So first, out of these 4n, 2n of these are the q minuses, so they're gone. So we're left with 2n. Okay? And then we will make some sort of Clifford algebra that will schematically take the form q. I'm keeping track of the indices in one direction, just one of the many planes. Q plus q minus will be equal to 1, because if you get a 1 on the right hand side, the charges have to cancel. So that the charge here will be minus of the charge there. Okay? So we could choose any 1-2 plane and choose the spins of that 2 plane to tell you whether you've got a creation or an annihilation operator. Okay? We make the plus spins, let's say, the creations, and the minus spins the annihilations. Let's say we do that. Okay, so in that 2 plane, I'm keeping track of the spins that occur in my representation. So all my creation operators now are plus spins. Okay, how many creation operators do I have? I have n of them. So what is my vacuum? May have some spin, but So let's say that the spin of my vacuum is S. I don't yet know what it is. But if I act with these creation operators, n q pluses on the spin S vacuum, the final state when I act with all of them will have spin is equal to S plus n by 2. Because each of these pluses carry spin half. Okay? Now, I'm going to want a Cpt conjugate representation. Everything will work out, so everything Cpt conjugate. So the highest spin must be equal to the lowest spin in magnitude. So S plus n by 2. N by 2, correct. So the highest spin, let's write this as half of 2s plus n. Okay? So how am I going to choose s so that we get something, highest and lowest? Let's take examples. Suppose n was equal to 1, then we would have to have two such representations. So we could choose, we would have to have two such representations to get Cpt conjugate. But let's take even n. Let's say n was equal to 2. Then the minimum spin content we could get is if we chose s to be minus half. Because if n is equal to 2, then when we act with both of them, we will get minus half, 0, and plus half. Acting with one of them will give us 0, and then we will get plus half. Is this clear? Okay? Suppose n was equal to 4. Then we could choose s is equal to minus 1. That would give us spins, minus 1, minus half, 0, 1, 0, half, and 1. In general, you see that the range of spins that we get, the difference between the highest and the lowest, is n by 2. Okay? Now, when do we necessarily exceed spin 1? We say that if n is greater than 4, we necessarily exceed spin 1. N equals 4 produced the smallest range of possible spins. Spins going from minus 1 to 1. If n is equal to 5 or higher, whatever we do, either we will get a spin more than 1 on the positive side or on the negative side. Okay? Because the range of spins is n by 2. Okay? And then we divide by another 2 because we can go from minus to plus. So that's n by 4. But if this becomes greater than 1, at least one particle will always have spin greater than 1. Now in ordinary quantum field theories, we do not know how to make quantum field theories with massless particles of spin greater than 1. This tells you that ordinary quantum field theories, at least with our current state of knowledge, will always have n less than or equal to 4. But remember that our total number of supersymmetries was 4n. So the total number of supersymmetries for ordinary quantum field theories is always less than or equal to 16. Okay? So although we can work out the general theory of representations of the supersymmetry algebra for arbitrary number of supersymmetries, in implementation in actual quantum field theories that work, and I emphasize quantum field theories, the total number of supersymmetries is always of this sort. We get doubling with superconformal, I'll tell you about that. But the total number of supersymmetries is always less than or equal to 16. Okay, so far so good for quantum field theories. Okay, how about for supergravity? When we know how to make sense of theories with spins, massless particles with spins greater than 1, up to 2, as long as we have gravity in the game. Okay? So then we're going to allow ourselves a range of spins that is 4. So n by 2 will be can be allowed to be equal to at most 4. Is this clear? Please stop me if it's not clear. Therefore n can be at most 8, but the total number of supersymmetries was 4n. So total number of supersymmetries then can be at most 32. Okay? So in any theory with more than 32 supercharges, light-like representations will always have at least one particle of spin greater than 2. We don't know how to make sense of any such theories, more or less. More or less. Light-like particles, so far we don't know how to make sense of any such theories. Okay, so light-like particles with spins greater than 2, we don't know how to make sense of. So total number of supersymmetries in supergravity theories always less than or equal to 32. Okay, and you remember the counting. It's useful to keep this counting in your head. Let's say take 32. Half of the supersymmetry is inactive, so that's 16. Half of them are creation, so that's 8. So the range of spins is going to be 4 minimum, because each creation operator carries spin half. But it can be symmetrically distributed from -2 to 2. Okay, that does it. Now this isn't the most favorable condition. If you chose some other representation, or you didn't start with the symmetrical vacuum, you'd go bust. So the best you could possibly do, okay, is to keep below, you have to keep below 32 if you want a theory with spins less than or equal to 2 for light-like representations. Okay, so while the number of supersymmetry algebras is actually infinite, because you can have more and more and more supersymmetries, the number of supersymmetry algebras that actually work for making quantum field theories is a relatively small number. And for work for making supergravity theories is a larger but also finite number. Okay? As many of you know, string theory in 10 dimensions, or M theory in 11 dimensions, maxes out that 32 supercharges. As many of you know, when we look at quantum field theories, n equals 4 Yang-Mills theory maxes out the 16 supercharges. So we have examples of theories with these maxed out things. We don't have examples of anything that goes beyond this. These arguments that I presented here well, at least suggestive. I wonder if there's some way around. But many 30 years of work, nobody's found theories with more than this. So maybe these arguments are just right. Okay, excellent. Questions or comments about this before we start getting our hands dirty?
Can you repeat the argument of this? Given an n, how you are calculating the spins?
How I'm calculating the spins. Okay, so what I do is I have to divide my supercharges into creation and annihilation. Okay, so I choose 1 2-plane and call everything with positive spin in that 2-plane. I call that creation. Then everything with negative spin in that 2-plane will be annihilation, because commutation relations always are things where charges cancel out. Okay, we'll give you the one on the right hand side. This is clear? Okay, so I start with some vacuum. So I build my Clifford algebra space. I've not so far done it in detail. Right, I've not given you what representations of SOD minus 2 you get by building this Clifford algebra. We will work that out in detail in many examples. But here I'm giving you a general feature. The general feature is this: I'm only keeping track of spins under that 1 2-plane. Okay? Now, when I build that whole SOD minus 2 representation, the vacuum that I start with by acting on with things will turn out to have some charge, some spin. I don't yet know what it is. I'll be agnostic about it. But I know that whatever that spin is, if I start with 4n charges, 2n inactive, n of them creation, so I can raise the spin by n by 2. Okay? Now, I'm trying to maneuver so that I get minimum possible absolute modulus of spin. So the best thing I can do, half. So that's n by 4. Is this clear? Okay? So it's a very simple argument to tell you that supersymmetry cannot be infinite. It's bounded in nature if you want physically acceptable theory. The main assumption is that, the point, you see it in front of your eyes. We're stopping at theories with spins greater than 1 for massless particles, for quantum field theories, and spins greater than 2 for gravity. If you can somehow get around that, then you can get around this also. But, it's formed a consistent picture so far.
But you also assume that the Cpt conjugate exists. But can you...
But suppose the Cpt conjugate does not. See, then I can start with... Okay, so I could start with a spin that was not so that it paired up. But then I only get worse. Because I move one side rather than the other, spins get higher or lower. So the case I looked at was the best case. Nothing you can do will be better than this. So I made an assumption, and you're right, but the assumption I made was the case that would help me the most. Is this clear?
And this is the assumption which is making it n by 4.
N by 4. This is the assumption that's making it n by 4. You don't want to make the assumption, and we don't need to, but you'll only do worse, right? Okay.
Absolute value.
Yeah. What this is telling you is the following. You see, one way of not making this assumption is by choosing some other representation R1 with which to pair. We will see. What this is telling you is that what I'm telling you basically is the following. That if you max out this case, let's say that we max out n equals 16 supercharges for quantum field theory, and we want representations in which only spins are always less than or equal to 1, then now we'll get basically a unique representation. Anything else you try to do will go out of that range. On the other hand, if n was equal to 2, you may have some play. You may get multiple such representations. What are these different representations? Well, different choices of this R1. Is this clear, Diksha? Okay. Questions, comments?
Mathematically, there's no problem in taking n to be any large. It's only the physics which dictates.
Exactly. At the level of algebras, we've already produced the algebras. They all work. Okay. In fact,
sorry, what is the physics problem?
Physics problem is that if you look for representations of these theories, at least if you have massless particles, at least in theories where you have massless particles. And we believe that massless particles are sort of important because at high enough energies, all particles look sort of massless, right? But at least if you have massless particles, then you will always end up, if number of supersymmetries is larger than 16, with massless particles of spins greater than 1. And basically nobody has found out a way of making consistent theories, quantum field theories, with massless particles of spin greater than 1. Do you remember what the problem was with making consistent quantum field theories with spin 1? The problem was an apparent clash between unitarity and Lorentz invariance, right? Because you write down canonical commutation relations. Okay, let me remind you of this. We write down canonical commutation relations. I don't think I'm being recorded anymore. So we write down canonical commutation relations like this. A mu dagger is equal to eta mu. Now, if this was delta mu nu, we'd be happy. Because A with A dagger, where one is creation, the other is annihilation, should have this sign with a plus. But we get this eta mu nu. So there are some oscillators that have the wrong sign. These are the time-like oscillators. That's bad. That would violate unitarity. Okay. And the way we deal with this is to introduce a gauge invariance. And that gauge invariance kills some of these states. Okay? Similarly with the gravity. You write down commutation relations and it looks like it's bad. Huh? Thank you. It looks like it's bad, but we can cure it by introducing a gauge invariance, namely diffeomorphisms. Okay? You try to do the same thing with massless particles. With higher spin, nobody's managed to make it work. Anything with spin higher than 1. You have to have enough invariance to get rid of all your negative norm states. Otherwise your theory doesn't make sense. It's quite a tight problem. People have tried hard and not made it work. So that's the problem. No, there are no guarantees in life. Maybe you can make it work. But people have not managed. Okay, let me take 5 more minutes. It's getting late. Let's take 5 more minutes and I'll be stop. Any other questions or comments?
There are no-go theorem kind of things too. Yeah.
There are some no-go theorems, right? There is these Weinberg-Witten type theorems. What did Weinberg and Witten prove?
So there are issues with interacting massless higher spins, but not the free.
But even the free guys, if they're massless, I suppose if they're free, yes, there is a gauge invariance. There's a free gauge invariance that gets rid of all the states. Yes, once you make them interact. Once you make them interact. Yeah, so that's correct. Free theories we can do quite a lot. Are there no-go theorems? There are these Weinberg-Witten type theorems which probably say something about higher spin theories. Let me rewind. Weinberg-Witten theorem, for instance, said that in any theory with a massless spin 2 particle cannot have a conserved stress tensor. Okay? And theories with gravity don't have a conserved stress tensor because they don't have local operators, because those are not diffeomorphism invariant. Okay? And I think that there are analogues of, tougher analogues of that for higher spin things. But all no-go theorems, as you know, Sunil, make assumptions. Right? For instance, people took Weinberg-Witten theorem to mean that gravity could not be people state it this way, that gravity could never be emergent. You cannot start with a quantum field theory and out from it comes gravity. Argument why? Because if you did that, then the quantum field theory has a stress tensor, because it's a quantum field theory. But then, by saying we get gravity, we have a massless spin 2 particle. But that contradicts Weinberg-Witten, which says that if you've got a massless spin 2 particle, you cannot have conserved stress tensor. Sounds like a pretty good argument, right? You can say it in 3 lines, keep it in your head, and what's the problem with that? Nonetheless, ADS-CFT is correct. You start with n equals 4 Young's theory, which has a stress tensor, and out comes gravity. And the point is that gravity comes out, but not in the dimension in which the field theory lives. So you don't have a bulk stress tensor, but you do have a boundary stress tensor. So all of these no-go theorems are correct in what the mathematics they state, but in the conclusions that they accomplish, you're limited by imagination. Who would have ever imagined that gravity could be emergent, but in some dimension that was, so if you took Weinberg-Witten to mean gravity cannot be emergent, you would have made a bad mistake. And a number of people took that to be the meaning, right? So what I mean is that between the actual, what is proved, and what you conclude, you should be very careful with no-go theorems. Always. Yeah. Okay. I think we're almost, let me just 2 minutes and we've gone somehow slow today, but okay. Let's 2 minutes start looking at the trivial examples. Then next class we can do the non-trivial examples. Let's start with d equals 2 and look at like-like representations. Okay, so now we've got d equals 2, we've got like-like representations, and so these z INs are 0. This guy is our algebra. Okay, what is the rotation algebra? So SOD minus 2, but d was 2, so it's nothing. Okay, so we don't have to worry about the rotation algebra. So all we have is this algebra. Sorry, this guy is gone. So all we have is this algebra. This algebra is exactly the same as the supersymmetry algebra, quantum mechanical supersymmetry algebra we discussed in class in some detail before the break. So like representations of the two-dimensional supersymmetry algebra are very, very simple. They almost have no structure in them. Okay, it's very similar to the discussion we had in the previous, in our before starting this semester. Okay, now let's move up one dimension. Okay, let's move up one dimension to d equals 3. Okay, once again we said p plus, like representation, we said p plus equals 0, sorry, not equal to 0, p minus equals 0, p plus something. We set z to 0. Okay, and this tells us that q minus with q minus is 0, therefore q plus with q minus is also 0, like we saw in general, but we see it very in our face in. So once again, the like algebra is only that of the quantum mechanical algebras that we talked about last time.
So the moment that you were taking the all spatial components.
We want like momentum. Suppose we took p plus and the spatial component, wouldn't be like.
Okay, sorry. Yeah. Then p minus would have come.
Yeah, would have to have yeah. So we're choosing a like momentum to be just in the p plus direction. Okay, so once again, if we take all zij's equals 0 and this like kind of thing, we get very simple algebra. Once again, the question of rotations is SO1. SO1 once again is nothing. So we don't have to worry about rotations, just once again like quantum mechanics. Okay, the first non-trivial case we get is when we have d equals 3 and we look at massive representations. Okay, so let me give this to you as an exercise for next class. Try to work out in the case of d equals, so now when we have d equals 3 and massive representations, we will have a little group algebra which is SO2. So rotations are not trivial anymore. It's very simple, it's abelian, but it's not trivial. Okay, exercise, try to work out the representations, massive representations for d equals 3. So massless representations, as you know, is following the general story. Half of the supercharges become inactive, there's no angular momentum, very trivial, just like quantum mechanics. Okay, try to work out the possible massive representations for d equals 3, allowing for an arbitrary central charge. We'll work this out in class next time, but try to do it yourself. Okay, and demonstrate that unitarity demands that the masses of all particles obey an inequality, and that inequality is of the form mass is greater than equal to something made out of central charge. Okay? And look specially at the representations where that inequality is saturated. Okay, this algebra is simple enough. You know, we just seen it in front of our eyes, right? There are no spinor indices hidden. It's just everything is there in front of you. Try to fool around with this algebra and see what you can do. Okay? We'll take this up next class.